Welcome to today's session. We are here to talk about a very modern paradox. Why is it that despite having more AI and digital twin technology than ever, many plants still struggle with basic reliability? Today, we're going to look at why technology must follow discipline, moving from asset hierarchies to governed metrics, and eventually to maintainable digital twins. Let's start with a scenario many of you know too well. Look at this pump, P204A. On the dashboard, everything looked green, yet the asset failed for the third time. The indicator was mathematically correct, but the underlying technical record was wrong. This is the green dashboard, red plant syndrome that happens when data doesn't match reality. Our governing proposition is simple. Technology is a multiplier, not a savior. If you multiply a 0 by 1,000, you still get 0. To get value, you need discipline in work processes, trust in technical records, and clear decision thresholds. AI and digital twins won't fix a weak maintenance system. They will only scale the discipline you already have. Think of reliability as an information chain. It starts with the physical asset and moves through identity, work records, and metrics before it ever reaches an AI model or a digital twin. If the identity link or the work record link is broken, no amount of sophisticated analytics downstream can fix the garbage coming in from upstream. It is vital to understand the hard truth of what technology can and cannot do. It is fantastic at capturing data at scale and finding patterns humans might miss. However, it cannot invent missing history. It cannot assign accountability for an alert, and it cannot decide which conflicting record is the truth. That remains the job of human discipline. Our roadmap for today follows 5 key questions. Can we identify the asset? Can we explain why it failed? Can we measure its performance accurately? Only after those are answered can we ask, can we predict its failure and represent it as a digital twin? Section 1. Identity before intelligence. We often treat asset hierarchies as clerical work or IT stuff. In reality, the hierarchy is the coordinate system for every work order and sensor. Without a solid identity, your data is just a pile of unorganized numbers. To build a proper foundation, we use standards like ISA 95 and ISO 14224. This structure takes us from the enterprise level down through systems and equipment units, all the way to the specific component where the failure occurred and the measurement point where the signal was captured. The golden rule of identity is to separate 3 things. Where is it? The functional location. What is it? The serial asset. And where did it fail? The component. If you collapse these into one field, history gets corrupted every time you swap a pump, and you lose the ability to track component-level reliability. Look at this before case for P204A. In the old system, it was just a water pump that was broken and then fixed. With this data, we have no idea what failed, no way to track parts, and no ability to map sensors. This asset exists in the plant, but it's invisible to the data. Now look at the progressive reveal of the same asset. We give it a stable address, a serial life history, a specific class, and a criticality level. Now, every work order, spare part, and vibration sensor lands on the exact same coordinate. This is the technical identity required for digital twins. To maintain this, you need naming rules that survive software migrations. Identifiers must be unique, persistent, and readable. Most importantly, they must be class-based and change-controlled, so that decommissions and merges leave a clear audit trail. Criticality is not just a label, it's a decision driver. High criticality assets require tight data controls and validated models. Low criticality assets can have leaner records. By defining the consequence and likelihood of failure, we decide how much effort we invest in the data for that specific machine. When identity is governed, the hierarchy becomes the join key for the entire technical ecosystem. It links the bill of materials, the work history, the failure codes, and the sensor tags. This is the foundation of the asset's working knowledge. Data cleanup campaigns usually fail because they lack governance. You must assign decision rights. Who owns the hierarchy? Who defines the equipment classes? Before you clean the data, define who is accountable for keeping it clean through the asset's lifecycle. We often talk about clean data, but clean means fit for the decision. We measure quality across 6 dimensions, including validity, timeliness, and context. As this chart shows, being complete isn't enough if the data is inconsistent or lacks the operating context. Data quality should be managed like a maintenance backlog. You profile the data to find orphans and invalid codes, prioritize them by asset criticality, and then fix them at the source. The goal is to make data exceptions visible to the people who can actually correct them. Section 2. History before prediction. A work order is not just a piece of paper for the accounting department. It is the plant's technical memory. If you want to use AI tomorrow, you need to record the technical history today. A truly useful technical record must answer 7 engineering questions. We need to know what function was lost, what was observed, why it happened, and, crucially, what proves that the restoration was successful, such as left vibration values. We need a closeout standard. It should be small enough that technicians will actually use it, but rich enough to learn from. This includes capturing the specific component, the failure mode, the resources used, and evidence like photographs or test results. One of the biggest mistakes is relying only on free text like pump add fixed to do analysis. We use codes to compare trends and narratives to preserve the technical nuance. Codes tell us external leakage. Narrative tells us the 2.1 millimeter soft foot found during alignment. In a failure taxonomy, we keep the problem, mode, cause, and remedy in separate fields. Don't let your data get messy by coding bearing as a cause. A bearing is a component, not a cause. Keeping these distinct allows you to see the difference between what happened and why it happened. A good code list is short for the technician, but deep in governance. If a technician has to scroll through 100 codes, they will just choose other. We keep it class-specific in version, so that historical meanings are never silently rewritten. Here is an example of an evidence-rich record for P204A. It doesn't just say it was repaired, it captures the leak rate, the vibration velocity, the root cause of pipe strain, and the as-left verification. This one record supports execution, analysis, and future AI training. When we talk about time, we have to be precise. One failure event triggers several clocks. There is a difference between active repair time and the total restoration time, which includes waiting for parts. Don't lump these all into one generic MTTR metric. We also need to count events by rule, not by the number of work orders. One failure event might generate 3 different work orders for inspection, repair, and alignment. If you count 3 failures instead of 1, your reliability metrics will be completely skewed. Section 3. Definitions before dashboards. A KPI is not just a pretty number on a screen. It is a governed question. Before you build a dashboard, you must define the formula, the population, and the specific decision the metric is intended to support. Always start with the business outcome. Are you trying to improve equipment availability, optimize workflow, or verify strategy? Your information metrics, like coding completeness, are the leading indicators that tell you if your outcome metrics, like MTBF, can even be trusted. Let's look at MTBF. It's simple math, operating time divided by failures. But the difficulty is in the eligibility. You have to be clear about what counts as a failure and what the observation window is. Do not mix planned interventions with actual functional failures. Be careful with fleet averages. A fleet average for MTBF can look like it's improving while your most critical assets are actually getting worse. You must segment your data by duty, environment, and asset class before you try to interpret the trend. For MTTR, specify what the R stands for. Are you measuring active repair, hands-on time, or restoration? The total time the asset was down? A plant can be great at turning wrenches, but terrible at logistics, and you need to know which problem you're solving. Availability is another metric that depends entirely on your perspective. Technical availability focuses on the equipment, but operational availability includes waiting, logistics, and whether the asset was even required. Define your boundaries explicitly. Backlog is a measure of work demand, not just a count of open orders. To understand it, you need to look at volume, readiness, age, and risk. Ready backlog, measured in weeks of labor capacity, is one of the most powerful indicators for maintenance planning. A stable total backlog can hide an aging risk tail. If 20% of your labor hours are for jobs older than 12 weeks, you have a growing risk of failure that an average number won't show you. Segment your backlog by age and criticality. Schedule compliance requires you to freeze the promise. You compare what was completed against what was on the frozen schedule at the start of the week. You also need to code the reasons why work wasn't finished. Was it an emergency or a lack of parts? High compliance isn't always good. You can manufacture high compliance by underloading the schedule, essentially making an easy promise. You must pair compliance with schedule loading and break-in work to see the true quality of your coordination. PM compliance should measure execution within the technical tolerance. Completing a monthly PM 2 months late isn't compliant just because the work order is closed. You must measure completions within the approved due window. A balanced view uses leading indicators to control the system and lagging indicators to judge the outcome. If your PM's inside window, leading, starts to drop, you can predict that your functional failures, lagging, will eventually rise. Every metric can be gamed, so you need guardrails. If you only track MTTR, people might stop the clock while waiting for parts. The guardrail is to show both active repair and end-to-end restoration time. When a KPI becomes a target, people will optimize for the definition. Finally, every metric needs a specification sheet. If the definition, formula, source, and owner can't fit on one page, it's not ready for the executive dashboard. Publish these definitions so everyone knows exactly what the numbers mean. Section 4. Decisions before algorithms. Predictive analytics is the hot topic, but it only creates value when you already have a defined failure mode and a work process ready to act on the signal. An alert that no one acts on is just noise. AI should be a closed-loop design. It starts with a failure mode and ends with a verified intervention. The value isn't in the dashboard signal. The value is in the verified repair that prevented a failure. Feedback from the field is what makes the model smarter. A prediction must arrive within a useful intervention window. If your model detects a failure only 2 hours before it happens, you don't have time to plan, order parts, and execute. The P-F interval is a planning constraint, not just a mathematical one. Don't jump to complex optimization if a simple rule-based threshold will work. As you move from anomaly detection to prognosis, the data requirements and operating risks increase significantly. Climb only as high as the decision requires. Maintenance data is notoriously difficult for machine learning. Failures are rare, labels are often weak, like fixed, and operating contexts shift constantly. You have to intentionally manage survivorship bias and context shifts to build a model that actually works in a planned environment. The economics of thresholds are vital. A model with 95% accuracy can still be a failure if it misses the 4 high-consequence events that cost millions. Choose your alert thresholds based on the cost of a false negative, missed risk, versus the cost of a false positive, unnecessary inspection. Always put a human in the loop. The model outputs a risk score, but a human validates it, decides the disposition, and creates the work order. The outcome of that work order must then be fed back into the model to close the learning loop. An AI model is a maintained asset, not a project you finish. It requires monitoring for drift, where the model's performance degrades over time as the plan changes. You must revalidate the model whenever the asset's duty or the sensors change. We recommend following the NIST AI Risk Management Framework. This involves governing the accountability, mapping the failure consequences, measuring the model's validity, and managing the risks of using AI in a physical environment. Before you pilot predictive analytics, run it through this deployment gate. If you can't define the failure mode, or if you don't have a workflow for the alert, you're not ready. A failed gate is not a reason to stop. It's a work package to fix the foundation. As we discuss AI, watch how the information hands off between systems. These video examples show digital twins and agentic AI in action. The question for us is, where does the owned work decision happen in these clips, and how is the result captured? Section 5. Purpose before the twin. A digital twin is more than just a 3D model with a fancy label. It is a governed, synchronized representation. If it doesn't help you make a decision, it's just a digital toy. Let's be precise with our language. A digital model has manual data exchange. A digital shadow has automated data flow from the plant to the model. A true digital twin is synchronized and used for simulation and operational decisions. Know which one you're building. A maintainable twin has 6 layers, from the physical asset up through identity, data, and models to the decision and action. Crucially, the twin must know the configuration version it represents. If the plant changes and the twin doesn't, the twin is lying to you. Choose your twin based on the value of the decision. Is it for what-if scenarios, for failure progression, or for simulating maintenance planning? Each of these requires different levels of model fidelity and data synchronization. You earn the right to a twin by passing readiness tests. If your asset identity is ambiguous or your sensors aren't traceable, the twin will fail. Be explicit about the economics. Does the value of the decision justify the cost of maintaining the twin? A digital twin creates a new trust boundary. You have to manage the integrity of the data pipeline and ensure that model changes are version controlled. If the model fails or data is unavailable, what is the safe fallback for the plant operator? Not every asset needs a twin. High-value, high-effort twins should be reserved for critical systems like compressors. A pump might only need an anomaly detection loop. Align your investment with the decision value and the effort required to maintain it. In a connected architecture, integrate by role. Don't try to build one giant system. Let the ERP handle finance, the CMMS handle work history, and the twin services handle the models. Use the asset ID and timestamp as the common threads that link them all. Maturity happens in stages. You move from invisible to recorded, then governed, and eventually twin-enabled. Prove each stage on one critical value stream before you try to scale across the entire plan. Evidence, not software labels, defines your maturity. In your first 90 days, don't try to fix everything. Choose one critical system and stabilize its information flow. By the end of day 90, you should be able to move from an identity to an alert and a verified repair without any manual data reconstruction. Over 12 months, scale by asset class and decision value. Only move from foundation to analytics and twins after you've proven that the data remains controlled and the economics survive real-world operating conditions. Technology succeeds where operating roles meet. Use a RACI matrix to define who is accountable for hierarchy, who is responsible for failure coding, and who owns the validation of the models. Without clear accountability, the system will deteriorate. As you leave today, ask yourself these 12 questions. If you can't distinguish between position history and serial history, or if your KPIs don't have owners, you have work to do before your next technology purchase. In conclusion, discipline creates trust. Trusted data creates decisions. Technology simply scales the result. The order of operations matters. Identify, explain, measure, predict, and then represent. Thank you for your time. For those who want to dive deeper into the standards, here are the primary references from ISO, ISA, SMRP, and the DOE that form the foundation of reliability information management. These references cover the more advanced topics of digital twins and AI governance, specifically focusing on the NIST frameworks for risk management and economic evaluation. Finally, all the visual media and case study data used in this presentation are credited here. Remember that the P204A records shown were composite examples used for teaching the principles we discussed today.